U.S. Army Corps Engineering, TI 8502, Air Force AF Men 321225, 1 March 2000. Technical Instructions for Railroad Design and Rehabilitation, Chapter 7. Road Crossing and Bridges. Road Crossing. Establishing crossing requirements and need for the crossing. Appropriate location check for the installation master plan of road crossing. Increased maintenance costs and safety risks. Number should be held at a minimum. A study being conducted to assess the traffic side of the conditions newly planned crossing or intended upgrading or rehabilitation. The study should include amount of character of the vehicle, traffic, train vehicle, operating speed, crossing angle, horizontal, vertical approach to the road, traffic, available sight distance from all directions for the vehicle approaching the track and the trains approaching the crossing. Previous accident, incidental history. These findings establishing crossing, protecting design requirements, designing steps. The main step in designing a road crossing and determining geometrical layout, selecting the crossing face of the flangeway design, designing of the drainage, designing the track section, determining the appropriate cross protection. See the geometrical layout. And the ideal geometrical is 90-degree intersection of the track of the road. From the best side of the angle, the slight ascending grades of the road approaches drainage should be always away from the track to reduce the flow of the surface water towards the crossing. 2. Avoiding crossing near the road intersections. Avoid locating crossing with either road or railroad curve. These typical threats result in poor sight and warning distances and conflicting super elevations. They often lead to long-term maintenance problems, poor performance, and crossing. 4. Where the road and railroad cannot cross the right angles, the angles should be kept at 60 degrees or greater whenever practical. For angles less than 60 degrees, additional warning and cross protection should be considered. D. Crossing surface and flangeways. Table 7.1 lists 10 standards. Crossing types 7 figures 7.1 through 7.10 show cross sections. Design details. These designs described and below. The recommendations for the application of limitations should be noted. Even for the most expensive crossing surfaces, the cost of building a track, especially with the new rail is installed, the road approaches are usually more than purchase, installation, and cost of crossing surface itself. Especially the roadway traffic, significant numbers of heavy truck passes over crossing where this vehicle speeds exceed 25 miles per hour. The main cost variable will probably be expected durability in crossing. Table 7.1, table the starting point of the matching of the crossing surface to the traffic requirements. Description of the crossing surfaces below. The focus of the most appropriate choice. The road street in classes A through F. The traffic categories 1 through 7 in Table 7.1 are shown in TM 5822-2, AFM 887. Chapter 5 entries the table, the code of the suggested crossing services. For the track, 6 and 7 have no. Well, 1 has 4A, 4B, 5, and the road street classes were the type of the category. Both A and B are the same except for part 5. C is pretty much the same except for part 4A in part 1, which gives an extra 2 and a 5 instead of the 4A and 4W and with a 4C. Traffic category 2, road class, street class D. Let's move on to the key table. Traffic category 1, up to 1% of the traffic of 2-axle trucks. 2, the 1 to 10% of 2-axle trucks. 3, up to 15% of traffic 2-axle trucks. Up to 1% of the tractors 3 or more axles. 4, the up to 25% of the tracks, 25% of the tracks is 2-axle trucks. Up to 10% of the trucks with 3 or more. 4A is more than 25% of the truck traffic at all types. 5 is tracked vehicles up to 60,000 pound gross weight. 6 is tracked vehicles up to 90,000 pound gross weight. Track 7 vehicles up to 120,000 pounds gross weight. Crossing type 1 is gravel crossing, timber flange way. 2 timber crossing. 3A asphalt crossing. 3B asphalt crossing, timber flange way header. 3C, 4 rail asphalt crossing. 3D, 6 rail asphalt crossing. 4A, cast in place concrete crossing. 4B, prefabricated concrete panel crossing. 4C, sectional monolithic concrete, no ties. And 5, full depth rubber crossing. Note, more detailed description of road street classes and traffic categories can be found in 5822 AFM 8887, Chapter 5, including the provision of forklifts. 3. Constructed surfaces. Crossing the type of 1 and 3A and through D and 4A may be categorized in constructing across a typical road street, basically extending the cross of the truck from the form of crossing separate flangeway. Headers may be used in the crossing generally made with the available road track and the materials fabricated on the side. The road arrangement provides a site-specific versatile to fit the crossing place at the time of the construction. These crossings are readily adapted to any track of the super evaluation gradient. Generally, these crosses cannot be readily removed or replaced with the track of the road maintenance is required. 4. Prefabricated surfaces. Crossing type 2, 4B, 4C, and 5 may be categorized as prefabricated. The crossing generally ordered with the manufacturer assembled at the side of the surface plants using the special panel attachment track fastening hardware. Prefabricated crossings are often required with longer ties than standard, must be ordered specifically for the size of the rail and tie plates anchors at the crossing and ensure the panel height, the width will match the rail height and the sufficient clear of the space available under the panels of the tie plates and railway fastening. Prefabricated crossings must be ordered to match the track curvature. Crossing angle vary significantly from 90 degrees and suggested prefabricated in order to extending 2 feet on each side of the beyond the widest part of the road through the crossing, allowing the cross angles as needed. Prefabricated crossings typically installed with more quickly constructed and usable installation complete. When considered, prefabricated crossings are suggested with the drawings and instructions obtained with the sample manufacturer to help determine the exact listing of the materials hardware required as well as available options, track construction, and preparation requirements. The typical Type 1 gravel crossing with timber flangeway. You see the we'll look at the top first. The normal width of the roadway, the end of the timber, the normal spacing, ties on 20 inches center from the new construction crushed stone. The road is the normal width of the roadway, the 2-foot minimum off the roadway to the end of the timber, normal spacing with crushed stone and C timber joint detail, which is the edge of the roadway, the elevation roadway surface 6 inches tight off 6 inches off the edge of the roadway with 2-inch minimum elevated roadway surface, elevator on top, elevation through the track and bevel detail. Slope of the required uniform transition adjacent to the roadway, 2.5 inches in between the railhead of the and the crossing of the crushed stone and existing roadway. The subgrade is 5% typical on the ballast underneath the ties. Rail tie plate is under the it's 2 inches under the edge of the roadway. The timber fastening the flangeway damage existing roadway drainage side for the ditches. Timbers may be cut in the suitable spacing of the maximum 4 inches timber. Intermediate joints, draggers, intermediate joints with 2 joints do not fall in the same tie. Apply fasteners at the end of the timbers as shown is less than 4 inches of the timber bears. The cross tie fasteners must be applied to the next cross tie. 4-inch, 2-inch minimum bearing distance fastener to the edge of the distance of the faster end of the timber. Standard staggered fastener 1 inch either side of the center of the bond timbers. Field side, gauge side, timber joint detail. Discrete construction subgrade, installation, subdrain, ditching, and geotextiles is required. This is a typical timber crossing. You see the full contour dope with the Hastek material, 3/4 inch timber fasteners, bevel timbers, pavement surface, roadway pavement, and plan. The bevel detail, top of the rail at the timbers, 1 inch, 1 foot by 8 inches. Counter bore is 2 feet 5/8 of an inch diameter with 1/4 inch depth and 3/4 inch by greater than or equal to 11 foot timbers. Top of the timbers at the top of the rail. Asphalt filler. New pavement surface. Existing railroad surfaces. Existing railroad base. Ballast of 10 inches minimum with a 5-degree type grade. Bevel into the drainage pipe of minimum of 6 feet. A field surface, road surface, 3/3/4 of an inch, 3.5 inch, 2.5 inches to 3.5 inch must be clear tie the plate of the gauge side, 2-inch minimum. Asphalt filler ties and field boring of 1/2 inch holes crossing timbers and cross ties before the timbers fasteners are installed. The flangeway detail. Typical 3A asphalt crossing. You have the roadway, the saw cut existing pavement with the bevel asphalt. See the details. Normal width of the crossing, saw cut existing pavement. Normal width of variable of 2 feet from 2 feet off the normal width of the road plan. The flangeway detail shows a minimum of 2 inches by 2.5 inches by 3 inches on the rail with 2 inches and a quarter inch asphalt pavement. To the asphalt pavement. The top of the asphalt is 1 inch by 8 inches. Detail the shape before the tie. Drawn not to scale. Saw cut existing pavement joint to be sealed. Existing pavement 5 feet typical to the center of the track. Flangeway. See detail from the existing pavement to the center of the track is 5 feet typical. Flangeway, see details existing payments. The ties has 10 inches ballast and then goes into a drainage pipe with 6 inches with 5% type of the subgrade. Reconstruction subgrade, installation, subgrade ditching, and or geotextiles is required. Okay, this one is a typical 3B asphalt timber flangeway. Shows the normal width of the roadway with 2 foot minimum as normal spacing of the tie end of the timbers. Normal spacing 2 feet minimum off the width of the roadway. Ties 20 center of the new construction. Asphalt as in the center of the tracks in between the railway. 1 inch clearance, 8 inches off the asphalt to the top of the asphalt. The flangeway detail shows the field side road surface 3.25 inches with the tie and 2.5 inches with 3.5 inches. Well, must clear to the plate of the gauge seal. Has asphalt filler filled with bore 1.5 inch holes crossing timbers, cross ties before timber fasteners are installed. The flangeway detail shows a 5 feet typical from the pavement to the center of the tie. Timber flangeways headers existing pavement and with a ballast of 10 inches and 5-degree type of subgrade into drainage pipes of 6 foot. Timber lines may be cut suited to the spacing of 4 foot to inch timbers intermediate staggered intermediate so that the 2 joints do not fall on the same tie. The 4 inches, 2 inches, and 2 inches distance. The deeping on the distance distance between the edge of the tie, the distance from the fastener to the end of the timber. Stagger fasteners either at the end of the bond of the timbers field inside and the gauge side. Apply fasteners to the timber shown in the less of the timber pairs. Cross-tie fasteners may be applied to the next cross-tie timber joint detail. Reconstruction subgrade, installation subdrain, ditching, and or geotextiles is required, not drawn, not to scale. A typical 3C4 railway asphalt crossing. Asphalt with the wire holding on by a threaded bolt for which is a scrap rail underneath the web of the head of the running rail, set with a double shoulder tie plate, which is holded by a threaded rod on a nut. The rail catches underneath the web of the other running rail. The scrap rail holded down by a double-headed plate with 1/4 inch from the asphalt with track spikes spiked in it. There's a track spike installed on the corner edge of the double header that holds the scrapping rail. Install threaded rods, riser plates, and every third tie cut the holes in the rod with torch. Use hot mixed asphalt compacted vibrator roller. Okay, this is a 3D railway asphalt. As you see, the asphalts are then gray with it shows a center rolling rail. Hold it with a down double threaded three stack of double with a space gap a flat piece. There's 3 double-footed ties which are anchored on the center rolling center one with the center rail, which is given a 2.25 inch scraping with 1/4 inch from 2 foot 4.25 inches from the rail center of the rail. The auxiliary scrap rail. The 5/8 of an inch cut of the tie plate with a 4.25 cut of the tie plate from 7 to 10.5 inch tie plate. with an 8.5 cut of the 7 3/4 and 11-inch ties, and an 8 3/4 cut of the 7 3/4 and 11-inch 3/4 tie. Only scrap plates can be used for cutting. Riser plates of 1A, 2A, and 2A may be selected needed to make tops, auxiliary rails, and 14 or fourth of an inch below the top running rails. Auxiliary rail, running rail and auxiliary rail shows from the overhead of the track spike reversed, not the track spike is reversed at the center. Plaque arrangement placed on every other through the crossing. Both ends of auxiliary rail to be cut and is shown at 6.5 or approximately 45-degree angle. For a cast in piece of concrete, you see the width of the flangeway, the 2 foot from the normal width of the crossing from the saw cutting existing pavement. Bevel concrete and timber flangeway, see the detail saw existing bevel concrete. Given a flangeway detail and detail and bevel, 5 feet from the typical center of the track, a depth of 2 3/4 of an inch from the existing pavement to the concrete pavement, which is ballast of 10-inch minimum, 5%. Number 2, 4 by 9-inch reinforced bars in each crib, drawn pipe reinforcement, cement concrete pavement. 7/8 typical prefabricated concrete panel. The gauge panel, the field panel with the center of the road replacement with the normal width of the road by 2 feet off the side of the crossing, variable with precasting lag bolt holes and typical pointed truss. The railway head is given a 2 inches by 2 inches. The concrete gauge panel, rubber filler, cross tie, typical flangeway, typical end plan. Panel, concrete 6-inch type with a 4-inch tip type. Saw cutting existing pavement to be sealed, 4 feet to 5 feet, typical to the center of the track from the existing pavement. The field panel, the gauge panel, the field panel, lag bolts. The ballast 12-inch minimum, 5% typical grade. Drain pipe 6 foot. Drawing not to scale. This shows the lag installed. 2 10-inch ties typical. Section 7-9 typical 4C section monolithic concrete, no ties. You see the section of modular crossing with an aggregated base course of subgrade holding on to a monolithic concrete piece. The rail flushing crossing of the surface is 12-inch minimum. There's a sealer in the center and 2 center bolts with base anchors inserted into the concrete. The type 5 full depth rubber crossing, field gauge panel fuel plan, the 45-degree angle of the new from the new pavement surface, road pavement, full depth rubber crossing pad at the top from tie to tie, full depth rubber elastomeric crossing pad, asphalt wedge end detail, field panel 1.5 inch. 1 foot 11 inches type, 2 foot 5 type to from the field panel to the gauge panel with these rubber plugs, 2 3/4 of an inch depth inside the rail head rail gauge with a 2-inch minimum of a 1 3/4 inch tip type. Ballast of 10 inches, timber fasteners, 5% typical subgrade into the drainage pipe of minimum 6 inches diameter. Flangeways. Generally, there is often in most maintenance-intensive parts of the crossing. In all crossing, clear and flangeway space must be allowed to impede the passage of flangeway to the railroad wheels. Open and closed flangeways, depending on location, opinion may vary whether the benefits of flangeway exceed their cost of disadvantage. Open flangeways allow water to the crossing track below, usually considerably highly desirable. However, the drainage is good when the water quickly runs and causes little harm. Over the time, the dirt and the debris enter the open flangeway may impede the drainage. Flat field flangeways are often subject to the rapid build-up dirt and debris and snow and ice. If unclean, these foreign materials are typically packed in the passage of the wheel. Flangeway builds up the point of the blocking the flangeway, causing the derailment. Icy flangeway, high probability causing derailment. In summary, the open flangeway readily allows the water to enter the track structure of the field. Flangeway must be typical and clean with a frequent in the areas of low annual rainfall where the track road gradients normally direct water from away from the crossing. Open flangeway design performed in most other cases. Filled flangeways will provide long-term benefits from reducing the amount of water entering the track from the flangeway. A filler material. Less desirable filler material is asphalt with inexpensive. It tends to break to the short time, losing an ability to seal against water entry and ultimately requiring time-consuming removal or replacement. Performed or pourable rubber products are available for some of the crossings. Rubber crossings typically can comment on the flangeway filler mold is in part of the panel. The concrete panel crossing often supplied with the rubber flangeway fillers is sometimes pre-attached with the panel's foam. Rubber fillers maybe have highly initial cost, but other responsibility seal against the water and entry, and the generally longer-lasting flexibility, reducing the tendency debris package flangeway to cause derailment. Rubber flangeway fillers are especially useful for one crossing geometry low relative evaluation naturally drain rainwater crossing flangeways where crossing drainage is naturally difficult. When crossing heaving the freeze of these cycles, the common problem of the rainwater snow melting enter in unseated flangeways. Rubber fillers are alternatives to the asphalt filler. Has not been held up in the past. Figure 7.1 shows a rubber flangeway installed in the concrete panel. Crossing. You see the field panel, the gauge panel with the rubber field side filler and a rubber flangeway filler, while the tri-side plate is spiked and under the field and gauge panel with a railway anchor. The following should be considered as selecting appropriate roadway surfaces: vehicle traffic volume, type of the speed, roadway use, streets using industrial traffic, speed vehicles, road traffic volume, type of the speed, accident history, existing crossing. The specific crossing surface may be contributed to accident costs, initial replacement costs, maintenance costs, and G expected the service of life. Type 1 gravel crossing, the timber flangeway header of the crossing, an appropriate location, locomotive volumes, the crossing not often large trucks and track vehicles. Type 2 timber crossing, the crossing generally medium lifespan of 10 to 15 years, often chosen due to long familiarity, experience of design removed in the track road of the maintenance. However, the warping stress that can commonly build up the wood long exposed with other elements may be replaced. The difficulty may result in rougher riding surfaces. Timber are subject to wear, where they gradually lead to exposure to the passing of the vehicle tire. So the timber is also subjected to damage by the plow blades during snow removal. Type 3A asphalt crossings, they are expeditionally and inexpensively constructed. By the absence of separate header of the flangeway typically leads to the difficulty in keeping the flangeway clear of the pavement and braking adjacent with the rail. 10. Type 3B, asphalt crossing with a timber flangeway header, with the presence of the separate flangeway header compared with the Type A. Typical results of reduced flangeway height and the maintenance less than the pavement breakage of the flangeway. Expected life may be averaged to 8 to 10 years using moderate traffic, and the freeze-thaw cycles are common. 11. Type 3C railway asphalt crossing design using the subject of the low plow blade during the snow removal operation. Type 39B, Type 3B crossing, it uses scrap rail turned in on its side from the solid flangeway. It tends to reduce the amount of water entering the track and can be cleaned out with the damage of the flangeway. 12, Type 3D 6 railway asphalt crossing. Protective rails on each side of the running rails take side of the lateral impacts of the passing vehicles to reduce the tendency of the rail losing and over the time of the vehicle traffic design. It may be used with a heavy track vehicles. Common crossing track design requires cutting many scrap type plates to act as support shims, but not as with typical Type 3C material type and inexpensive. 13. Type 4A cast in place concrete crossings. They may be suited for the track and be paved across the track. Truck delivery across the warehouse through the concrete material storage age. The type of the crossing throughout the durable than an asphalt is most typical. All types of the remove access to the track is needed. 14. Type 4B prefabricated concrete panels. General characteristics: they are normal producing number of the manufacturers that are being widely adopted due to the relative strength, expected durability, ease of the installation, removal of the track, maintenance, moderate cost. The crossings are not subject to decay or are standard timber crossings, much less subject to damage from snowplow. blades, or snow removal operations compared with timber, rubber, and gravel crossings. In addition, they must be suitable accommodated with traffic for traffic vehicles. When either a traffic or adjacent road maintenance is required, the crossing can be removed relatively easy and part of the whole replaced without a damaged crossing material track without loss of or original evenness of the surface. Like other crossings that require solid support to prevent panel breakage from the loss of the crossing and surface of evenness due to the stiffness of the panel. These crossings are not recommended for the location where pronounced vertical curve in the track. Specifications. Design crossing that varies the manufacturer suggested with the type chosen, the minimum concrete strength of 500 psi with guaranteed panel thickness variation within plus or minus 1/8 of an inch with a waterproof chemical resistant seal and panels with the option of epoxy coated rebar. Warranty of the crossing performance should also be obtained. And install options. In standard legal installation of the panels are lagged attached with the wood ties, the lag bolts not fastening with adjacent panels similar to the way of the conventional timber crossing installed. With the lagless installation, the field panels go to the panels fastened lengthwise to the three monolithical panels of the length of the crossing. No fastening in the ties. Different methods of using the panel to panel fastening. Each angles other than a end of the resistant devices must be used to secure the cross longitude. Vertical lateral movement is prevented with the weight of the fastening panels combined with the confinement between the adjacent road with the railway field, the panel confinement between rails of the gauge panel, the lagless installation flagway fillers, and must be kept the panel secured away from the running rails for the military application. The lag installed in suggestion figure 7.2 shows lagless concrete panel crossing adjacent with the panels fastened in short series of short welds. The lagless control panel crossing shows the field panel, the gauge panels, the rail, the end restraints, the recessed lifting ring pockets with steel angle bar and panel ends the center over to the tie with welded connection between the panels. Type 4C is a section monolithical concrete. The construction, the crossing is essentially form of the concrete roadbed. Crossing surfaces are one of the complete unit. The rail rests on the rubber pads of the pre-concrete sections from the solid bed. The concrete bed rests on the layer of the crushed rock over the prepared subgrade. The crossing may be suited for the rail service through active container handling area whether the track would be normally run through the concrete paved area. They would be warranted whether the heavy truck traffic or the other crossing type have not withstood traffic or loading. These crossings are railway accessible, unboltable, removing upper gauge panels. However, the boy bed is solid. The truck cannot be surface tamped or raised in conventional methods. Surface correction of the typical raise may be done at equipment, either completely removing the cross section and altering subgrades for the small corrections. Pressure injection grout beneath the section. Subgrade of the base of the material. Adequate strength of drainage is essential for the good long-term performance of the crossing. They are most expensive 10 crossing types, generally about twice the cost of the concrete panel type 4B crossing. 16. Type 5 full depth rubber crossing. Like concrete panels, they are made of the separate panels, the rest of the ties, and fits around the rails. Flangeway rail fillers are built into the panels while most be fastened in the tie lags. Some design are available for the lagless installation. Rubber crossing provided flexible surface, and the flexible prevents the spreading of the heavier wheel loads over the large area made of the running in the tie paths where the traffic is heavy. Snow plowing operation can be often damaged. Rubber surface is most durable, made completely with what is termed virgin rubber. The other option, recycled reconstituted rubber, is less expensive but not suitable for large traffic volumes or heavy truck traffic. Drainage. All crossings, all surfaces require sub-drainage similar to the shown in Figure 713 and 714. Geotextiles surrounding the pipe filter and optional, recommended in fine particle soils with clogging the filter occur. Type 713 is geotextile sub-draining the vehicle road crossings. You see the 5-foot typical center from the end of the existing pavement, vertical distance of from the ballast to 12 inches through the sub-ballast to the drainage side ditches with a compact subgrade existing pavements and track. This shows a typical drain road crossing, the side ditches and the slope drain to the drain. With the rail tracks through the road, through the rail tracks, and the sub draining just kind of like across. Track design. Any other crossing surface prefabricated construction do not alone. Other performance depends on adequate support of the ballast to some grade. Unless recently done with the track, ballasting selection and drainage system must be first rebuilt and prepared in subgrade before installation crossing. The drainage must be effectively transmit water outside of the crossing level. When crossing are built and rebuilt, all ties crossing itself at least 20 feet beyond each end of the crossing should be replaced. It's recommended for the wood ties of the road crossing, the 7-9 inch in cross section prefabricated road crossings insulated with tie length and spacing should conform to installation requirements provided by the cross manufacturer for the road crossing having heavy volumes of rail traffic or heavy vehicle traffic. It may be desirable installed in tie pads between the tie plates in the construction area shown in Figure 715 with the concrete panel crossing. The full length should always be nailed to the ties with 1 inch of the roof panel properly supporting the panels. Most manufacturers recommend the supply pads of the crossing. A rail anchors 4 spikes in each plate. A tie plate rubber pads optional and new ties through the crossings. In crossing of the main running tracks, rails of 115 pounds per yard is greater is preferred. As bolted rail joints the road crossing, often maintenance problems are recommended that all joints the crossing for 20 feet either end of the crossing be welded. As alternative, 80 feet of the joint rails readily available may be used to eliminate the crossing area. 6. If the track approaching the crossing anchored by the recommended each of the tie and the crossing box is anchored by the normal anchoring pattern maintained thoroughly without remainder of the crossing area, the 20 feet at each end. Once a conventional crossing surface is placed in the track will be covered maintenance and difficulty costly through the track geometry. Gauge surface and alignment should be near perfect before placing in the crossing surface. The ballast in and all around the tie should be compact to prevent settlement to movement of the crossing. 8. The crossing flangeway should be a minimum width of 2.5 inches with a maximum width of 3 inches and it be at least 2 inches deep. Road approaches. To reduce the amount of runoff water directly toward the crossing of the road approach is the best way to slope away from the crossing. To achieve the smooth riding crossing, the road approaches the slopes is best kept in the limits shown in Figure 7.3. However, the difference in the elevation between the railroad and adjacent roads may require steeper approaches. Ascending road approaches must not be steep and long flatbed tractor trailers, for example, long ground clearances might contact with the clearance. On descending the road, the approaches the gradients must successfully lengthen the stopping distance of the vehicle approaching the crossing, including allowance for the icy pavement. 7.16 is recommended crossroad approaches. As you see the level between the end of the 2 feet from the gauge of the head of the outside of the rail, you see 30 feet going down, 30 feet across off the level, with the road surface at 1% to -2%. 30 feet and off at 1% plus or 2% above the grade. Crossing protection signs and signals. Specification minimum requirements. Specification basic design appearance of the crossing. Warning signs, pavement markings, warning signals is given in Part 8 of the Manual Uniform Traffic Control Devices US.FHWA. All road crossings will have a minimum of standard warning shown on the MUT CD. These needed additional signs as flashlight, gates, and depending on the cross visibility, traffic character, volume, crossing geometry, accident, incident history. As described, further guidance providing crossing warnings protection can be found in the FHWA Railroad Highway Grade Crossing Handbook. 2. Visibility criteria. Clearly visibility criteria for the approaching stop vehicle is shown in Figure 7.17 and 7.18. If the distance of A, B determined in Table 7.2, the crossing considerably visible, unobstructed triangular defining distance AB is sufficiently clear that the motorist can see the approaching train anywhere with the field of view. Crossing that do not meet the clear visibility criteria may require additional protection. You see the outer field view from the road, and B from the approaching vehicle to the other outer field views. This is a clear visibility of stop vehicles. The stop line out of the field view of B and 1 at 15 feet from the track. Clear visibility distances for crossing vehicle speeds of 10 to 55 miles an hour. with clear sights at 70 feet at 10 miles an hour, 100 feet at 15 miles an hour, 20 at 130, 20 miles an hour, 135 feet the clearing distance, 25, 175 feet, 30 miles an hour, 225 feet sight of the distance, clearing of approach vehicle, type 35 miles an hour, 275 feet of the distance of approaching vehicle, 40, 350 miles, 350 sight of the distance, 45 miles an hour, 420 clear sight of the distance, 50, 500 clear sight of the distance, and 55, 600 clear in its distance. Clear track visibility beach from approaching vehicles. This shows the from 60 to 600 in a with every five, and train speeds up to 10 miles an hour with vehicle speeds in 5-degree increments gives a 10%, a 10 add 10 to the distance feet from 10 miles an hour to 10. Vehicle speed at 60. 15. Just add the train speed by the vehicle speed. Starting at the numbers 10 for 60, 15 for 90, 20 for 120, 25 for 150, 30 for 180, 35 for 210, and 40 for 240. Add the train speed by the vehicle speed for the original 10 miles an hour. For each 5 will increase the same as amount of speed in miles per hour for each vehicle speed in mile per hour. Clear track visibility distance B from the vehicle, the 15-foot stop line, train speed is limited 10 miles an hour. Visible distance of the distance of a 15-foot stop line is 200, 15 is 300, 20 is 400, 25 is 500 feet. 330 speed, train speed is limited to 30 miles an hour. Visibility distance 600. Train speed limit 35, visibility distance of B 700, and train speed limit of 400. Train speed limit of 40, visible distance of B should be 800 feet. Traffic characteristics, tractor character, volume, additional protection, desirable crossing. At the experience of the 2 or more train movements per day, production train movements range. Average daily vehicle traffic exceed 3,000 traffic threshold, drops 1,000 for the crossing, considering a visual obstructed defined above flashing lights or even gates should be considered crossing through. Experience several daily train movements, heavy truck traffic, frequent hazard material traffic vary where clear visible criteria are not met. Crossing geometry, crossing the road track angle on less than 45 degrees where the road approaches the track at a stepped grade and may call an additional protection. 5. Accidents, incident history, crossing experience, at least one accident. Some close call incidents. Whether incidents or motorists are not obeying the existing warnings or comments should receive consideration. Flashlight or gates or flashing lights already present. I. Whistleblow. Generally, whistle posts are signs located adjacent to the track incident with the road crossing ahead. The mark of the point standard horn signal crossing approach began with the whistle point. Most commonly shown in the just a large W on their face. Both various designs have been used. Installation operating rules may be designed. Designate type of those signs required. 2 to location. While the whistle post usually located on the right side of the track when viewed on the facing of the cross, the distance allows a significant time for the warn motors that the engine of the train and the track machine is approaching the crossing. The designer should consult with the state of the Department of Transportation installation requirements of whistle position and location. And the appropriate location will depend on the factors including speed, railroad traffic, speed vehicles, visibility, crossing, and commonly using guidelines, crossing warning signal being sounded at least 20 seconds before an engine, car, or track machine reaches its nearest end of the crossing. 2 bridges. Type of the railway bridge is classified in the deck type: open deck, ballast deck. The typical open deck bridge either four-tie is bolted directly to the structure, thus affecting the track, and becomes part of the bridge. The ballast deck bridge standard track ballast section is supported on the solid floor of the ballast deck. The advantage of lowering the track across the bridge to be lined and surfaced in the same fashion as the standard of the track. B. The design procedure. When the bridge is required for the bridge structure, design and practicing railroad engineering in accordance with the REMA Manual, Chapter 7, the timber Structures, Chapter 8, the concrete structures, Chapter 15, steel structures, Part 9, ARIMA, Chapter 15, provides background commentary, railroad bridges, design and practices. Basic design. The design of the railway bridges is based on two main factors: magnitude of load applied to the bridge, expected level of traffic, number of stress cycles over the design of the life of the bridge. One stress or load cycle is defined in one application, releasing a load on the bridge member. The D Copper E series loading design live load expressed from the Copper E series loading configuration about the Marima 1905 figure 17 and 19 illustrates the E1 axle loading. Higher loading is obtained, but the multiple each load of the same constant wheel spacing do not change. The E60 loading would show the largest axle load at 60,000 pounds. You see the axle center spacing, the engine 1 and 2 in the cars, the axle loading of 1,000 pounds. And 100 pounds a foot. To allow easy comparison, the permissible in-service loading or rating over the life of the bridge loads are used to original design compare effect with different engines carrier loads. If either design rating railroad industry kept in the basic copper load configuration used to represent all bridge loading and bridge capacity ratings. Equivalent copper loading. In loading of the train, typical of the heaviest common cars, the design of the train is converted to the copper E loading when having the same effect of the bridge. For the design of the train, the equivalent of the copper loading E value will vary from the train operation speed, bridge span length, the bridge design, and actual load distribution, and from the current trains will differ of the copper configuration. Equivalent to the copper loading will constant with all bridge components. Figure 720 shows the relationship between equivalent copper loading at 60 miles per hour. Pin length of one type of the steel bridge at loading shown in the figure 721 as example of 720 indicating 60-foot span of the train of the figure 721 produces equivalent to the copper E48 load of the respective floor beam reaction, and E57 load with respect to the shear, and E60 with respect to the bending moment. Variation of the copper E value span with the span length of the floor beam of the per reaction and shear, the bending movement, and the equivalent copper load. Axle loads, axle center spacing in feet, engine 1, engine 2 in cars, loading design for the train of 100-ton box cars. ARIMA standard fatigue stress cycle. The fatigue standard ARIMA design assumes the stress cycle of 100 trains per day that within 150 cars each load up to 315,000 pounds gross weight, traveling at a speed of 60 miles per hour every day for 80 years. Design live load standard ARIMA fatigue with especially high. Most military railroad bridges should be designed live loading. Table 7 when based on recommendations Chapter 5, 15 Part 9 of the ARIMA manual. Loading general recommendation span lengths of up to 75%, 75 feet. Actual design live loading may be adjusted accommodating span and lengthening structural design characteristics of other variables. The annual traffic volume in a million of the gross is 0 to 5 to 5 to 15 to E 100 tons E4 is 0 to 5 ton minimum million gross, 120 tons E50, 140 tons E60, 15 to 12 the recommended copper design load for car capacity E60 at 100 tons, E65 at 120 tons, E72 at 142 tons. Note 1 million gross tons approximately equals 7,600 loaded on 100 ton cars at 5,300 loaded up to 140 ton cars. Traffic over the military railroad design does not exceed 5 million gross tonnage per year. The 0 to 5 million gross tonnage category of the table 6 to 8 usually applies to exceed the lower level of bridge would experience an average annual passage of 38,000 loaded 110-ton cars, 104 per day, or 26,500 loaded 140-ton cars, 73 per day throughout life of the bridge. Walkways. When the bridges are located in or areas which switch movements are made at either location are either usually necessary for the people to walk alongside the truck or the cars. Walkways must be provided at least one side of the bridge, where the people must have the access to both sides of the track. When bridge occupied, walkways must be provided on both sides. Workers must never be expected to cross the track by going under the cars or crossing over the couplers or climbing over the cars. Tie pads, open deck bridges, installation rubber tie between the tie and tie plates is recommended. Chapter 8 Terminals.